In previous chapters, we have used single values to approximate a population. And in the last chapter, we saw that if we take the mean of the sample means, that in fact equaled the population mean. It was an unbiased estimate of the population mean. And so we're going to start in this chapter with mean, because it is the most unbiased point estimate of the population mean mu. Now, what we're going to do, however, is use that point estimate to create what's called an interval estimate, a range of values used to estimate the true value of the population parameter. Sometimes the confidence interval is abbreviated CI. We're going to use the point estimate as the center of the interval and then add and subtract a margin of error. Now, two things that sound very similar: confidence interval and level of confidence, sometimes called the confidence level. This is associated with the interval estimate, and it is the probability of success in the process to construct the interval estimate. The level of confidence is the probability that the interval estimate actually contains the population parameter, assuming the estimation process is repeated a large number of times. The level of confidence, C, is the area under the standard normal curve between the critical values negative ZC, so a negative z-score, and its corresponding positive z-score. So really what we're talking about is the probability of being between those two z-scores. The confidence level is often expressed as 1 minus alpha, where alpha is the complement of the confidence level and is the probability that the confidence interval actually contains the population parameter. For a 95% confidence level, alpha is 0.05. Now, a couple of things to note here. A level of confidence of, say, 95% refers to the process, that if many different samples are collected, all the same size, and the corresponding interval estimates are constructed, the probability is 95% of these interval estimates would contain the true value of the population parameter. Also, a level of confidence of 95% does not say there is a 95% chance the true value of mu, since we're starting with mean, will fall in the interval estimate. It also does not say that 95% of the sample means fall within that interval. What it's saying is, if we construct a whole bunch of intervals, again, that's the process, 95% of these interval estimates would contain the true value of the population parameter. Now, we already mentioned critical values. Those are the z-scores that bound the area we expect the value of the true parameter to fall. So, critical values are values separating sample statistics that are likely to occur from those that are unlikely to occur. In general, beyond the z-scores, they are unlikely to occur. The number ZC is the critical value. That is a z-score that separates an area of 1/2 of 1 minus c in the right tail of the standard normal distribution. And the negative is the critical value. That is a z-score that separates an area on the left. Now, and we'll go over some examples shortly so that makes a little bit more sense instead of just this definition. We are going to start in this chapter with the confidence interval for mean, for mu, where sigma is known, and then we'll proceed to where we don't know sigma, which is the most common situation. Now, there are some requirements for this process to work. Okay, first off, we need to know the standard deviation for the population. We need to know sigma. Either the population is normally distributed or n is greater than 30. We have seen that kind of requirement before. After requirements are met, a C confidence interval can be determined as follows. We're going to use table 4. That is the standard normal distribution table. to find the critical value ZC, the z-score, that's the critical value. Then we'll use that to find the margin of error, which is based on that z-score and on sigma. And then note, here's that square root of n that we also saw in a previous chapter when we were looking at the standard deviation of a group as opposed to the standard deviation of just for one individual. And then we can build, once we have our margin of error, we can build our confidence interval by adding and subtracting the margin of error from our point estimate. And then usually we round to an extra decimal place. You don't need to carry all those decimal places. Now, one last thing before we get to some examples is you can rearrange the margin of error equation in terms of n, so n equals the other three parts, and that can give you a minimum number to sample, the minimum sample size needed for that particular margin of error. So anytime you hear about a margin of error for some poll on TV, note that is always related to the sample size that they took to create that poll in the first place. All right, so let us look at some examples now. First off, what is the confidence level if alpha is 0.1 or alpha is 0.2? Against the confidence is 1 minus alpha, so 1 minus 0.1, that would be 0.9 or a 90% confidence level. If alpha is 0.2, 1 minus 0.2 is 0.8 or an 80% confidence level. Now, how about finding the critical value, the critical z-scores? And we're going to do it for the 95% and an 80% confidence level. So kind of going in the opposite direction from what we just did in part 1 there. So let's look at these two cases. Alpha is 1 minus the confidence level, so 1 minus 0.95 gives us 0.05. Remember that that 0.05 is split on both ends of the normal distribution. So in the right tail, we would have 0.025, that's 0.05 divided by 2. But notice this is in the right tail for a positive z-score. So we have to subtract from 1 because table 4 only goes to the left. 1 minus 0.025 gives us 0.975. That's to the left. When we look up 0.975 in the table, it tells us the z-score is 1.96. So basically in that situation for a 95% confidence level, our critical values would be a negative 1.96 and a positive 1.96. All right, how about for the 80%? Well, 1 minus 0.8 is 0.2. Half of that is 0.1 in the right tail. Again, we need area to the left, so 1 minus the 0.1 gives us 0.9. When we look up 0.9 in the table, we see a z-score of 1.28. So for this confidence level, we expect the parameter to fall between negative 1.28 and positive 1.28. All right, let's look at some examples to construct some confidence intervals. So, for weights of men, a random sample gave n equals 40 and a mean of 172.55 pounds. Again, x bar is the mean. Research from other studies suggests the population of men's weights have a standard deviation of 26 pounds. So here our sigma is known. Find the best point estimate of the mean weight of the population of all men. Construct a 95% confidence interval estimate of the mean weight of all men. First off, x bar equaling 172.55. That is the best point estimate of the population mean. That's going to be the center of our interval. Okay, now we need to find E, the margin of error. So that's going to be the critical z-score times the standard deviation over the square root of n. In the previous problems, we found out that a 95% is a z-score of 1.96. So 1.96 times the 26 divided by the square root of 40. Again, that was the sample size. Gives us 8.057. So I went to 8.06 for my margin of error. To then create the interval, it's the mean subtracting the margin of error and the mean plus the margin of error. So 172.55, subtract the 8.06, 172.55 plus the 8.06, and now we have our confidence interval. The true value for mu should fall within that range. Alright, now let's look at an example where we want to find the minimum sample size to have a particular margin of error. So, suppose we want to estimate the mean IQ score for the population of statistics students. How many students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Well, first off, with that 95%, our alpha is 0.05, which will lead to our z-score, our critical value of 1.96. It says within 3 IQ points, so the margin of error is 3. And in an earlier chapter where we were looking at IQ scores, sigma is 15. So again, I took the margin of error equation, rearranged it in terms of n equals, plug in our numbers, and we get n is 96.04. So in this particular case, you'll always round up because we want to make sure that it is no more than the margin of error listed, so no more than 3 IQ points. In other words, 96, if we had plugged in 96.04, that would have given us the 3. By plugging in 97, we get a little bit less than 3. All right. Let's look at a second example of finding our confidence interval. The mean braking distance of a simple random sample of cars is x bar equals 137 feet. So again, x bar, that's the mean of the sample. We want a 95% confidence, n is 32, and sigma is known to be 7 feet. Find the margin of error and the confidence interval. So here is our margin of error equation. Again, it's 95%. So that gives us a critical value of 1.96 times the 7, which is the standard deviation. The sample size is 32, so the square root of 32. That gave us 2.43, rounded it to 2.4. Now I'll construct our confidence interval. 137 subtract the 2.4 on the minimum side, 137 plus the 2.4 on the maximum side. And so our interval is from 134.6 to 139.4. Okay, let's look at a second example for determining the minimum number. How many cars must be randomly selected and tested to estimate the mean braking distance of registered cars in the U.S.? We want 99, so this time it's 99% confidence that the sample mean is within 2 feet of the population mean, and the population standard deviation is known to be 7 feet. Now, since we have a 99% confidence, our alpha is 0.01, so then when we cut that in half to 0.005, look up the appropriate z-score, we're going to get 2.575. Again, we want it within 2 feet, so our margin of error is 2, sigma is 7, plug them in, we get 81.23, which gives us, rounding up, an n of 82. That would get us within 2 feet. 81.23 would be exactly 2 feet, but a little bit higher, and we are inside of 2 feet. And then finally, let's look at our last example, and then do a little bit of an interpretation, if you will. A random sample of red blood cell counts of 50 adults is obtained. The sample mean is 4.63. The population standard deviation is 0.54. Find the best point estimate of the mean. Construct a 99% confidence interval estimate of the mean. If the normal range for males is 4.7 to 6.1, and the normal range for females is 4.3 to 5.4. What does the confidence interval suggest about these normal ranges? Well, first off, X bar is 4.63. That's the best point estimate of the population mean. Here we find our margin of error. Again, since it's 99%, that came with the z-score of 0.2575 times the 0.54, the standard deviation, divided by square root of the 50. We get 0.197, rounded it to 0.2. So we have our interval 4.63 subtract 0.2 and 4.63 plus 0.2. And so here is our interval estimate of the population mean. Now, our males went from 4.7 to 6.1. So all of this, almost 4.4, 4.7, so not quite all, but a lot of it, of this range, is within the normal range for males. On the other hand, this 4.3 to 5.4, all of this is within the range for females. So it's partially in the male range, wholly within the female range, so the mean is roughly in the normal range for a population. And so there you have it, constructing confidence intervals where the population standard deviation, where sigma is known.